And you guys are here today. We're missing a few people. I'll go ahead and tell you right up front. You're going to have a question like this on your first exam. Yeah, I always put a question like this on my first exam. And what's hard about this isn't necessarily the difficulty of the individual problems. It's deciding what are you supposed to do in each instance, in each question. What trick are you supposed to do? And sometimes when you're working through all the MyMathLab problems, because you do all of the limits at infinity problems all at once, and then you do the limits with the square root problems all at once, you don't get a lot of variation in these problems. And so that's really the hard part here. And I want to make sure you understand what the strategy is as we work through these types of questions. So before we talk about limits, before we do anything with limits, here's a function. What is the most important thing about a function that you should always be careful of? What do you say, folks?
The denominator can't be 0?
Well, I mean, sort of. That's a consequence of what we're asking here.
Its domain?
Yeah, I think I would argue that maybe the most important thing about a function is its domain. Okay? So let's go ahead and identify the domain of this function. And to do that, maybe we need to factor the function. I can factor out a 3x. That leaves me with x plus 4. And in the denominator, that factors as x plus 4 times x minus 4. So here I think we can identify the domain. What's the domain here? It's a set of x such that what? Go ahead and everyone jot it down what you think the domain is. You could write it in interval notation or set-builder notation. I don't care which. But this is the first thing I think we can do to sort of start separating these types of problems up, right? So for example, I gave you a whole lot of room to work question number A here. But if we look at the limit as x is approaching 0 from r of x, we now have the right vocabulary for this. After the pre-work that you guys did last night, we now have the right vocabulary to say, how can we think about this function? Well, the function r of x is continuous continuous at x equals 0, so direct substitution, the direct substitution property applies. So that's the same thing as just evaluating r of 0, which would be 3 times 0. Actually, we'll put it in the original format of it. So we'll put it in 3 times 0 squared plus 12 times 0 all over 0 squared minus 16. And this evaluates to 0. Questions on that, folks?
It's continuous because 0 is within the domain, correct?
Yes. So another way to say, yeah, great question, Daniel. Another way to say that is this is a rational function and it's continuous everywhere it's defined. Yeah. And so because it's continuous everywhere it's defined, and I'm asking you a limit question for where it's defined, the direct substitution property says rather than doing the limit question, just substitute it into the function. Folks, there's lots of ways you could show correct work for this problem. Okay. All right, let's look at B. Okay. Question B, I'm going to go ahead and say this is a section 2.5 question. I don't expect you to necessarily know the section numbers in this class, but you know, it helps you to sort of separate the types of problems that you're dealing with. This is where we look at the limit as x approaches infinity. So what are we looking for? What we're actually looking for is what is the behavior of this graph as you move far to the which way?
Right.
Far to the right. Yeah, I think, Robbie, you were going to say that too. It looks like you were on mute there when you said it. Yeah, as you move far to the right, how does this graph behave? If I want to look at the left-hand long-term behavior, I'm going to plug in negative infinity. Okay? So, folks, I don't necessarily think you have to show all this work for this problem, but I'm going to anyway. And I think you should too as you're writing this down right now because you've got nothing better to do. And then we'll talk about it. When do you need to show work, etc. But I think that based on what you guys did in college algebra or your pre-calculus class, you should be able to look at this question and spot what the answer is. That's always a helpful thing in math, being able to spot what the answer is. Okay? What is the answer to this problem? What's this limit going to come out to be?
3.
Yes, I didn't see who said that. Was that Marshall? Yeah.
It was.
Great. Yeah, so the answer to this is 3. Okay? The trick from college algebra said, look at the ratio of the leading coefficients. Now, folks, one thing that's hard as you come into calculus is to separate what's just a nifty trick from what is accurate mathematics, correct mathematics. Okay? That's just a college algebra trick, and you're welcome to use that trick. Okay? But I can guarantee you I will ask one problem on your test where that trick won't help you. It doesn't apply. And so you have to know this other method of finding the behavior as x approaches infinity. So what is our strategy rather than using that trick, which you could use on this problem, and if you just went ahead and said the answer is 3, I'd give you full credit. But because you know that I'm going to ask you a problem where you have to show this other work, or otherwise you won't get the right answer, what's my strategy here, folks?
Multiply by 1 over x squared.
We're going to multiply this by 1 over x squared to the numerator, and then what we do to the denominator, we have to do the denominator. So both the numerator and the denominator by 1 over x squared. Tough question. Why is it 1 over x squared? Because there's a squared in the numerator, or because there's a squared in the denominator?
Denominator.
Yeah. So our strategy is to always multiply by 1 over x raised to the highest exponent seen in the denominator. Great. Okay. So we go ahead and clean that up. And we get 3 plus 12 over x in the numerator divided by 1 minus 16 over x squared. Okay. Folks, if I really wanted to be pedantic, I would distribute that limit to both the numerator and the denominator, and then I would distribute it over the sums and differences. But eventually we get to we're going to use the fact that 1 over a large positive or large negative approaches 0. Okay. So put another way, I'm out of room here, but let me just say it. If I took the limit as x approaches infinity of 1 over x to the third, or the limit as x approaches negative infinity of 1 over x squared, that's going to be 0, right? In both cases. And that's one you can, I think, so I've hopefully scared you guys a little bit with this concept of infinity. And I've hopefully scared you guys a little bit with these indeterminate forms. Okay? But this is something that you can rationalize your way through. And that works. 1 over a large positive number, or 1 over a large but negative number, is going to approach 0. Okay? So this gives me 3 plus 0, because this one right here looks like what I just described, all over 1 minus 0, again, because this piece right here looks like what I just described. And so we get a limit of 3. Now, folks, did I ask for the horizontal asymptote here? No. Now you should see that asking for this limit and asking for the horizontal asymptote are very similar questions. They're two sides of the same question, but do make sure you answer what I asked. Okay? Don't give a horizontal asymptote if I don't ask for it. And don't just give me the limit if I ask you for the horizontal asymptote. You got to put those two ideas together. Okay. Oh, so let me just reiterate. So again, for this problem, if you just went from here to here, I would give you full credit for this question. But do know that I'm going to ask a question on the exam where you can't just do that. Okay? The ones where that happens is specifically the ones where you've got either square roots or absolute values, where you have square roots or absolute values inside your rational expression. That's where you've got to be very careful. Okay. We've got 2 more to go. Notice that these, actually 4 more to go, but these next 2 questions have to do with what? We initially identified the domain, and I'm having you go explore what's happening what's happening around those exclusions in the domain. At this point, given that 4 is just a standalone excluded value from the domain, we know x equals 4 is a vertical asymptote or a hole. Okay? And the same thing for x equals -4. We know that much. We know we're going to have a vertical, and I guess I should say, or both, because you can have both a vertical asymptote or a hole. We know it's going to be one of those options for each of those exclusions in the domain. Now what do we have to do? We have to justify which one it is. Folks, it is not justification to say because they cancel, it's a hole. Now, you've got the right idea. You're on the right track, but that's not your justification. The justification in this class is always a limit. Okay? All right, so let's go ahead and do it. So let's look at the limit as x approaches -4 from the right of r of x, and that's the limit as x approaches -4 from the right of, and we factored it, I think it factored to be 3x times x plus 4 all over x plus 4 times x minus 4. Check me, folks. Did I get that right?
Yeah.
Great, thank you. So at this point, yeah, we've already done all the hard work in that the hard work of this problem has nothing to do with actually writing this limit out. It has to do with the discussion that, or maybe it wasn't much of a discussion. It had to do with what I was saying as I was talking at you just a moment ago. That was the hard work of the problem. Because at this point, this is kind of old hat, right? You should be feeling pretty comfortable with this idea. Okay. We now evaluate this thing through direct substitution. We get -12 over -8, which reduces down to 3/2. But what have we just shown here, folks?
As we approach that limit, we go to the y values approach a fixed point.
A fixed point, exactly, a fixed value of 3/2. So as Marshall said, as our domain values approach -4, specifically from the right, as our domain values approach -4, our range values approach 3/2. That's that coupled with the fact that I forget what we were doing, -4. That coupled with the fact that -4 wasn't in the domain, those 2 bits of information together are enough to say that there's a hole in the graph there. Now, if -4 was in the domain, you'd have to check to see, well, what's f of -4, and you'd have to figure out whether or not that hole gets filled in by the definition of the function or not. It would depend. Okay, that's a question of continuity, which is what we're looking at today. Great. You can tell when I get excited, folks, I talk really loud. If I'm ever talking too loud, just tell me to quiet down. Send it in the chat saying you're talking a little loud. All right. Let's look at the next question. We've got the limit as x approaches 4 from the left of r of x. Hey, folks, I've had people say, do I need to re-show how everything cancels? And the answer is no. Now, if this were a standalone problem, I would like you to do that. But yeah, you've already showed some of this work, so if you want to go ahead and take this straight to 3x all over x minus 4, because that's going to help you talk about this problem easier, be my guest. You don't have to rewrite that work. Okay? Now, I argue that question C and question D are 2 completely different questions. I think that they are 2 completely different questions. What was the form, what was the structure of this question here as x was approaching -4? Now again, we identified the domain, and we said -4 is excluded from the domain, so right away we knew we couldn't do direct substitution. Not at least not off the right, not at the first step. But if we were to substitute -4 into the numerator, we would get a 0. And if we were to substitute -4 into the denominator, we would get a 0. So this is the justification that we've got that this problem had an indeterminate form 0 over 0. And whenever you see that, all you can conclude is that you can't conclude anything other than to say you've got more work. More work to do. Okay? Notice that in this case, this just had this is just a regular, just a fraction. So by the time we get down to here, we're able to do direct substitution. But when we started the problem, we couldn't say anything else other than this had the indeterminate form 0 over 0. And we knew we had more work to do. Now, this other problem, let's look at this other problem. In fact, I'm going to go ahead. I know I said I was going to write, but I'm going to go ahead and put this in here. You don't need to change that if you didn't. But let's go ahead and look at this. Before we did any cancellation, just to reiterate, this has what? Not the indeterminate form, but the form a over 0. So right away we know that the answer is going to be infinity, minus infinity, or does not exist. Where the does not exist usually happens if we ask for the limit proper, and that'll happen when, if the left and right hand limit disagree, but both of them or one of them is infinity. So anyway, we go ahead and clean this up, and we get the limit as x is approaching 4 from the left, as I had written before, 3x over x minus 4. And here's where you can just give the answer. Folks, when it has the form a over 0, I'm not going to expect it, I'm not going to critique you on your work, as long as you don't write anything dead wrong. Okay? Meaning there's no steps that you're going to show that will justify this. You can just go ahead and go straight to the answer. And in this case, the answer is negative infinity. Now, I think that you probably ought to give yourself a little bit of a justification for this, but I don't require it. The justification is that what was the numerator approaching? The numerator was approaching 12, and the denominator was approaching a small negative number, and so that approaches negative infinity. Notice I didn't write that in line with the equal sign. I don't have to write it at all, but that helps to kind of rationalize to you guys, you and me as we're having a conversation, why I wrote negative infinity as my answer. Okay. So at this point I've answered all 4 of these questions, and each one of them was slightly different. Okay. That's why I like this question so much. I will often, and I've told you, I will ask this question on your exam. Up to some variation, and if you want some different opportunities to practice it, look at the exam review, and then look at the 4 exams that I have posted. And you'll see that problem shows up everywhere with always a little bit of slight variation. Okay. So what I would say is, if you're feeling okay with these questions here, you're on the right track. Okay, there's a lot of tough tricks that we've shown, but it's better to have the big picture strategy and then start saying, okay, now what trick do I need to practice more, rather than to just kind of be diving into individual hard problems and getting through them, muscling your way through them. Okay. All right. We still have a couple more questions. Notice that we've done the work to show that at x equals 0, not x equals 0, at x equals 4, there's a vertical asymptote. Okay. Please, folks, I do say in equation form. When I say in equation form, I mean that you can't just put 4, because you haven't shown to me what you know by a vertical asymptote. Okay, so by the way, what was it that justified that we had a vertical asymptote at 4? The fact that the limit came out to be plus or one of the limits, the left or right hand limit or the limit proper, came out to be plus or minus infinity. That's the justification that you've got a vertical asymptote there. Did we look at the limit coming from the other way? No, we could have, and if we had, we would have gotten positive infinity, I think. Okay. State any vertical asymptotes, or excuse me, state any, oops, oh, folks, I'm sorry. Maybe some of you were noticing this. I put that in the wrong spot. This is vertical asymptotes. I'm sorry. Any questions on that? Somebody want to stop and double check that?
Could you just redo the explanation?
Yes. I'm very sorry, folks. I thought this said vertical, and I just didn't look at it. Vertical asymptotes occur whenever the limit as you explore a fixed domain value, not as you explore infinity, but as you approach a number in the x direction. If you get infinity or minus infinity for either the left, the right, or the proper limit, either of those outcomes, if you get plus or minus infinity, then you've got a vertical asymptote there. Okay. Folks, we've also shown that we have a horizontal asymptote at y equals 3. That was the work that this justified for us. Now, have I done all the work to show that the only horizontal asymptote is y equals 3? Have I done all the work to show that? Cole's shaking his head no. Why are you shaking your head, Cole?
Well, I mean, you didn't look at negative infinity in that end behavior.
Yeah, so we've only looked at the right-hand end behavior. Now, for a nice, well-behaved rational function that doesn't have any square roots in it or doesn't have any absolute values, you won't. I mean, if you check the left-hand behavior, nothing different's going to occur. You'll just replace this piece right here. You'll replace with negative infinity, and that won't make any difference because whether x is approaching a large positive or a large negative, that expression still goes to 0. So you'll still get the same answer of 3. Now, again, I've already hinted at, and you guys hopefully have looked at those in your 2.5 notes, there are some problems with square roots in them specifically where you get a horizontal asymptote as you go one way and a different horizontal asymptote as you go the other way. And if you're short of coming up with a very fast example for that, just remember the graph of your arctangent curve. The graph of your arctangent curve looks like this, and it's got one horizontal asymptote at y equals pi over 2. That's for the right long-term behavior, and it has another horizontal asymptote at y equals negative pi over 2, and that's for the left-hand long-term behavior. Okay. Okay, folks. I'm going to talk about the group. Oh, let me stop the recording.